Sending a single push notification is trivial, but processing 1 million requests per second causes naive system architectures to collapse entirely. At enterprise scale, this system must handle everything from an Amazon shipping update and a Netflix movie recommendation to a time-sensitive banking one-time password. The core function is straightforward. Accept internal events from various microservices, map them to specific user preferences, and interface with external service providers to deliver the messages. Functionally, this requires support for multiple communication channels, primarily push notifications, SMS, and email. Secondary functional requirements dictate that the system must support delayed scheduling and strict message prioritization. The true test lies in the non-functional requirements. We are designing for 1 million transactions per second across a base of 100 million daily active users. Under this load, the system must remain highly available. While eventual consistency across nodes is acceptable, the latency overhead for checking routing rules and user preferences must stay under 10 milliseconds per request. The engineering challenge lies in guaranteeing at least once delivery. You cannot drop a payload midway through processing, and you cannot accidentally spam a user with duplicates due to a network timeout. This diagram shows a naive, synchronous system design. All internal service requests route directly through a single central notification system block to reach third-party providers. This monolithic approach creates an immediate single point of failure. If this central node goes down, the entire notification pipeline halts. Furthermore, synchronous connections to third-party APIs, like Apple Push Notification Service or Firebase Cloud Messaging, introduce unpredictable latency. A slow response from an external provider will cause connection timeouts, backing up internal requests and ultimately crashing the server. To resolve this bottleneck, we replace the monolith with this decoupled, distributed architecture. The flow begins when an internal microservice triggers an event, sending it to the API gateway. A fleet of internal notification services receives the request, performing basic validation on the payload. These servers immediately query the database and cache to fetch device tokens and specific user notification settings. Once validated, the server constructs the final payload and pushes it into a dedicated message queue, immediately returning a success response to the internal service. Finally, dedicated worker nodes asynchronously pull these messages from the queues and execute the network calls to the external API providers. Decoupling the API receiver from the delivery workers transforms a fragile synchronous trigger into a highly available asynchronous processing pipeline. If we zoom in on the application codebase inside those worker nodes, we have to establish strict design patterns to handle future extensibility. Hard-coding delivery logic creates a brittle system. Every time a new communication channel emerges, engineers would have to rewrite core routing functions, risking regressions. We prevent this using the factory pattern. A central notification factory evaluates the incoming payload string and instantiates the correct object, like an email or SMS notification, without exposing the instantiation logic. We then apply the strategy pattern, implementing a send strategy interface to dynamically select the delivery mechanism at runtime. If the business requires a new channel, like WhatsApp, engineers simply write a new handler that implements this strategy interface. The core routing logic remains completely untouched. Before dispatch, payloads often require dynamic mutations. Using the decorator pattern, we can take a base message interface and wrap it with layers like a timestamped message or an encrypted message. These decorators enhance the message content consistently, adding tracking IDs or security tags without ever altering the underlying payload structure. Enforcing strict object-oriented patterns at the application layer protects the codebase from calcification as business requirements inevitably expand. Between the API receivers and those highly optimized workers sits the message queue, the ultimate shock absorber for the entire architecture.
When selecting a message broker, the choice typically comes down to RabbitMQ versus Apache Kafka. RabbitMQ pushes messages into memory and deletes them immediately upon consumption. While fast for lower volumes, it requires massive clustering to maintain millions of transactions per second, increasing operational complexity. Kafka is a distributed event streaming platform. Instead of keeping messages in memory, it relies on sequential disk I/O, writing events into an append-only log to maximize overall throughput. Instead of the broker pushing data, Kafka consumers actively pull from specific partitions. Each worker maintains its own offset tracker, recording its exact position in the log. This architecture maps directly to our system's prioritization requirements. We can isolate traffic by directing payloads to distinct Kafka topics. Critical alerts, like one-time passwords, route to high-priority partitions with dedicated worker pools to prevent login blocking. Promotional emails route to lower-priority logs. Relying on a partitioned, pull-based log ensures that sudden ingestion spikes buffer safely on disk, never overwhelming the worker pools or the downstream external APIs. Even with perfect internal scaling, edge case failures are inevitable. Third-party APIs will eventually throttle your requests or experience total outages. To handle this, we implement stage-aware exponential backoff. When a payload fails, it is routed to a dedicated retry topic with a progressively expanding wait timer. Increasing the delay multiplicatively, waiting 1 second, then 2, then 4, then 8, gives the degraded external service the necessary time to recover. Routing failed attempts out of the main processing pipeline prevents a retry storm, protecting the external provider from an accidental distributed denial of service while healthy traffic continues to flow. If a payload exhausts its maximum retry limit, it is routed to a dead letter queue. The dead letter queue isolates the unprocessable message and preserves critical metadata, like the failure reason and timestamp, allowing engineers to manually review and remediate the issue without silent data loss. Crucially, the entire retry loop must be idempotent. Workers must guarantee that reprocessing a delayed event does not result in duplicated state mutations, or worse, sending the exact same text message to a user twice. This schema details the one-to-many relationship between users and their registered devices. Before any payload reaches the delivery queues, the system must validate the recipient. The notification servers query these tables to verify if a user has explicitly opted in to the specific notification type, or if they are currently inside a Do Not Disturb window. To prevent overwhelming a user with alerts, we implement rate limiting using a token bucket algorithm, typically managed in memory with Redis, to strictly cap message frequency. True system resiliency is twofold. It protects your external providers from system-generated traffic storms, and it protects your end users from notification spam. This architecture diagram represents the complete production-grade system, integrating message delivery with authentication, rate limiting, and analytics. At enterprise scale, tracking the delivery data is as critical as the delivery itself. We use an analytics service to capture telemetry at every step. Workers log discrete flags into a data warehouse the moment a message is enqueued, and again when the provider confirms delivery. On the client side, the application returns interaction flags, logging exactly when a user opens or clicks the notification. Reviewing the flow, internal events hit the API gateway, where notification servers authenticate requests, validate preferences, and apply rate limits. Kafka buffers the workload by priority. Finally, idempotent workers pull from the queue, execute requests, and route persistent failures to the dead letter queue. System architecture is entirely dictated by scale expectations. RabbitMQ provides a functional, low-latency solution for a startup. But at 1 million transactions per second, a partitioned log like Kafka becomes mandatory. Ultimately, a production-grade system is defined by its asynchronous fault tolerance. It ensures critical data survives, queues, and delivers long after the initial trigger.